All right, so today's November the 21st. A couple of announcements here at the beginning. Your web assigned homework, you have a next group of web assigned homework is due on November 27th, so that's in 6 days. So that's, I guess, next Monday. So let's get started on that if you haven't gotten started on it, so that you get these last few assignments done on WebAssign. The Exam 3 review is online on my Google page, and a very thorough review it is. So please be looking at that review and be spending some time with it over the next week or so. Exam 3 window goes from November the 30th through December the 5th. So that means that the exam will start next Thursday. Do also remember that I'm going to allow on the Exam 3 and the final exam, I am going to allow the use of a scientific calculator. So not a graphing calculator, but a scientific calculator. So take note of that if you want to take advantage of that. Online office hours, remember that's Tuesday, which is today, from 8 to 9 p.m. And then no hours tomorrow and no hours through the week, through the weekend. But then again on Sunday, I will be online Sunday from 7:30 to 9. And then next Monday, again from 8 to 9. Oh yeah, and also today for your class, I guess, let's see. Yeah, so today I would be online from, I think it's 1 to 2 today, if I'm not mistaken. So 1 to 2 p.m. today also. All right, so I'm just checking to make sure that that's actually correct, that I'm going to be there 1 to 2 today. So yeah, right. All right. And then on-campus hours, I will be on campus next week, November 29th and November the 30th. I'm going to go ahead and post or send out a weekly update later in the Thanksgiving weekend to give you the exact hours I'll be on campus. Probably it'll be November the 29th in the afternoon, late afternoon, like 4 to 6, and November the 30th sometime during the morning hours, I'm sure, on November the 30th. So I'm not exactly sure the hours I'll be on campus, but those will be times that you can come by and get help. The final exam, remember that final exam testing window opens like right away after the Exam 3 window closes. So the Exam 3 window closes on Tuesday, December the 5th, and the final exam window is going to open on Thursday. So it's going to open up pretty quickly after that. The review for this exam will be posted this weekend. So if you want to see a final exam review, sometime during the weekend, I will be posting that. And then let me remind you about college algebra in the spring. Make sure that if you have to take college algebra in the spring, make sure that you get registered for that. I've been trying to remind everybody. And Sandra, I did see your name on the list, so I'm thrilled that you're there. Charlotte, I think I saw your name on the list, so that's awesome. And so if you haven't signed up for college algebra in the spring, regardless of who you're taking, please get registered for that so you have your choice of sections. And don't forget that I am teaching 2 online sections in the spring. It doesn't make any difference. If you do want to take one of those, it doesn't make any difference which one you sign up for. It's going to be the same class, just a different section of it. So I would encourage you, if you think that this format has worked for you okay this semester, to sign up for college algebra in the spring with me. That would be great. Today we're going to do more with domains and ranges. We started talking about functions last time, and so we're going to do more with domains and ranges from graphs, and then we're going to be talking about reading other information from graphs, and then we will look at graphing functions. We'll talk about plotting points to graph functions, and we'll look at x and y intercepts and look at some examples with that. So I think I'm going to go ahead and get started with this, and then this will give us a chance to do some reviewing from some things that we did last week also. So that's good. So we're going to go ahead and get started with domains and ranges. And so if you remember from last time, when we're talking about a function, remember that the domain is the set of x values that we're using in the function, and the range is the set of y values. Remember that if you have a function is a relationship where there are no repeated x's. So between two ordered pairs, you never have two ordered pairs that have the same x values. And also remember that repeated y values are okay. So if you're talking about a graph, just on a coordinate system, on a plane, right, the domains, you have the x-axis here, so those are the domains. That's where the domains live, is on the x-axis, and this is the y-axis, and that's where the ranges live. Also remember that when you're talking about domains, you also will frequently see these referred to as the input values and the ranges as the output values. I don't think I mentioned those words last time, but that's common to see the domain listed as the inputs and the range listed as the outputs. All right, so you've got remember how we talked about this last time then, as far as analyzing a graph and looking at its domain and range, being able to read the domain and range from the graph. We talked about walking along the x-axis for the domains, and you always walk from left to right. And as you're walking from left to right, what do? You look up and you look down vertically. And when you see the graph, wherever you're located, then if you see the graph, then that x value is part of the domain, right? So you're just sweeping across with this vertical line, basically, is what you're talking about doing. And then with ranges, you're doing exactly the same kind of thing, but instead of walking along the x-axis, you are climbing the y-axis, right? And so you're climbing up the y-axis. You're always climbing from bottom to top like this. And in this case, when you're climbing up the y-axis, now you're looking to the right and looking to the left. And the question's basically the same, as if you see the graph as you're looking to the left or to the right, then the y value that you're located at is part of the range. All right, and so we talked about looking at doing this for different kinds of graphs, and we started talking about writing out these domains and ranges in interval notation. And so that's what we want to look at today, is kind of pick up with that and look at maybe a little bit more complicated examples than what we saw last time for domains and ranges. So that's the first thing we're going to do. And then from there, we'll kind of move on. So let's look at this graph. Let's say I have a graph, and let's put it in blue. And we're going to start off with a simple graph. Let's say we have a graph that is just this line segment right there. Now, this graph, remember the number of points that are on this graph is infinite, right? Whenever you sketch a graph, anytime you put a curve, no matter how short that curve is, as soon as you start drawing a curve, you have an infinite number of points. Doesn't matter how long the curve is or anything like that, you have an infinite number of points on there. Because remember, a point has no width, no height, no length, no depth to it at all, no dimension at all to a point. It's just a precise location. So there's an infinite number of them on these graphs. All right, so this first graph right here, first of all, does it or is it satisfy the definition for a function? And remember, one thing we talked about last time is, does it pass the vertical line test? So I will ask you that question on the test. I'll give you a graph and say, is this a function or not a function, right? And so this is a function, right? This graph is, because it passes the vertical line test, right? But anytime I draw a vertical line, it only intersects the graph in one spot. All right, and so then the domain and the range. Now remember, the solid dot means that that point is part of the graph, and this point is at -3, -1. And then the open circle, which I've got at 2, 3, means that that point is not part of the graph. All right, so the domain on this function, and you know, since it's a function, we could name it, by the way, so we might name it f. Then the domain of f, which we would write with a capital D with a subscript of f like that, we would get that by doing exactly what we talked about in that graph right above, is we're walking along the x-axis from left to right, and it's whenever we see the graph vertically, right? Whenever we see the graph vertically, then that x value is part of the domain. And so what happens here? As we walk from left to right, we start seeing the graph here at -3. And I could actually sketch a little interval on the x-axis. And as I'm sketching this, right, all of these points are all part of the domain, aren't they? Because I can see the graph vertically from all these points. Until I get to 2. And then at 2, I can't see the graph because of that open circle. And then I don't see it anywhere after that. So if you do that, you've got this nice little picture of the domain. And so we can write the domain here for this graph in interval notation. It starts at -3. -3 is part of the domain, and so I put a bracket around the -3, and it goes every x value until you get to 2. And at 2, it stops, and 2 is not part of the domain, so I put a parenthesis around the 2. All right, and so that's the way I would write the domain in interval notation, is bracket -3, 2, and then close it off with a parenthesis. All right, so the range on f, you're doing exactly the same thing as you did with the domain, but now we are climbing up the y-axis. So here I am climbing up the y-axis from bottom to top, and so then I'm looking left and right. And as I look left and right, you know, I start marking where I see the graph, and I start seeing the graph right here at -1. And then up the y-axis, I continue to see the graph either to the left or to the right, in this case to the left. And then I see it to the right, right here. And I see it until I get to 3. And then at 3, I don't see it, and so I put an open circle there. And so that green interval there along the y-axis is a nice picture of the range right there. And then in interval notation, we would have started seeing the graph at y equals -1. And -1's included, so we put a bracket. And then that goes all the way, every y value, until you get to 3. And then at 3, we put a parenthesis like that. So we've got the domain and the range. So what have we done now? We've talked about a couple things from this graph. We've talked about the idea that this graph passed the vertical line test, so that means it's a function. We've been able to write the domain and the range down for this particular function. We can also we talked a little bit about this last time, but not a lot about it. I want to talk more about this today. We can start reading function notation from this graph. So for example, in this particular graph, f of -3, right, remember what f of -3 means. You're talking about the function f, right? That's just the name of the function. This is saying that the function f takes the x value -3 and it assigns it to the y value -1. What do? You look where x is -3, which is right here on the x-axis, and you see what the corresponding y value is there. In other words, you're trying to locate a point where the x value is -3, and you get -1. Right, so f of -3 is -1. It's because that point is on the graph right there, -3, -1. So I want you to also be able to read function notation from graphs as well, if it's a function, obviously. All right, So unless somebody shouts at me, I'm going to continue on. We're going to do another couple of problems like that. We're going to look at some different examples of graphs here. So there's one right there. All right, so the next example. So now we're going to start changing things up a little bit about the way these graphs look. So this next graph, we'll say has an open circle here at -3, 1. And then this graph comes down here to this point, which is at 0, -2. And then this graph continues on like that. And notice there's an arrow at the end of to the right on this graph. Where that arrow means that the graph continues on like it's been going. All right, now we did not see a graph that had an arrow like that last time, so this is our first experience with this. So first of all, is this a function? That's our first question. And the answer here again would be yes. This graph passes the vertical line test. So then the next question is, what's the domain? So let's name this function, by the way. Since it's a function, we'll name it g. So the domain of g on for this graph, right? We're using this little idea that we've just talked about where we're walking along the x-axis. So we walk along the x-axis and we're going from left. Remember, always from left to right. You're looking vertically. And what happens? You first start seeing the graph, not at -3, but just as you pass -3. So we put an open circle at -3, like that, because you can't see it at -3, but then when you go past -3, you can see the graph vertically. And you can see it for all of these x values. Now, this is where you have to be careful. Can I see it like right here at 4? Can I see it? Well, yeah, right there you can see the graph. So certainly 4 is part of the domain. Can I see it at 5? Clearly, yes. Now, what about at 6 and 7 like that? Now, at first you might say, well, no, I can't see it at 7. But remember that's an arrow right there in that graph. That means that graph continues on in that direction like it's been going forever, right? So this graph continues on like this forever. So yeah, at 7, you can still see the graph. And in fact, notice no matter how far I go off to the right here, I will always see the graph. So I just put an arrow at the end there. All right, so when that happens, when you're going off to the right and you've got an arrow like that, you would use an infinity symbol when you're writing interval notation. And if it was going off to the left, you would use a negative infinity symbol. And for the y's, it's going to be the same. On the bottom, if you're going forever and downward, this is going to be negative infinity in this direction. And for the y's, it would be positive infinity in this direction, like this. All right, so the domain in this problem starts at -3, but -3 is not really part of the domain, so I put a parenthesis around the -3. And then to the right, it goes on forever. And so this would be an infinity right here. And so in interval notation, it's going to be from -3 to infinity. Now, when you put an infinity down, when the graph is going infinitely far in one of the directions like that, you always use a parenthesis. Always use parentheses around infinities. Around infinity symbols. You never put a bracket there around an infinity symbol. Because a bracket implies that the graph actually stops at a specific spot. Infinity is not a number. It's always included inside parentheses. Okay. All right. So now we're ready to tackle the range in this problem. So in the range, let's see. I've got a bunch of stuff written on the graph, so I'm going to be climbing up the y-axis, but this time from on the left side of the y-axis. So So we're climbing up the y-axis, going from bottom to top. And the first place we see the graph, remember, we're looking left and right when we do this. And the first place we see the graph is here at -2. And you actually see the graph at -2. That's a solid dot. And now we start seeing the graph. In fact, we see the graph twice in here. That's okay, remember, to see the graph twice, because that just means you have repeated y values, and that's not a problem when you have a function. Now, when we get past, so this keeps on going, but when we get past 1 right here, now we can only see the graph once off to the right. It doesn't matter how many times you see the graph, as long as you see it, then that y value is part of the range. And again, you've got that arrow. The graph continues on forever, doesn't it? Going up like that. And so you always see the graph. No matter how high you go, you are always going to see the graph in this case. And so for this function, the range on g is going to be a bracket at -2, because -2 is part of the range. There's a solid dot there. And then this is going to go to infinity, right, forever in the positive direction, in the positive y direction like that. And so that's my domain and range from this graph. All right, and then some, so let's read some function notation off of this graph also. So first of all, if we had g of, and the graph has gotten kind of messy here because of all this stuff I've been drawing on it. So if you want, maybe not a bad idea to kind of re-sketch the graph over here. And so if I re-sketch the graph, let's see, it was started here at -3, 1. So here's -3, 1, down here to 0, -2, and like this. Right, so there's my graph. So if we looked at g of 3, for example, from the graph, then remember what you're doing is you're locating where 3 is on the x-axis, because that 3 represents a domain value or an x value. And what does this function do with 3? Well, you look up at the graph and you get that point right there. And so g of 3 is equal to 1. Right? You're just reporting the y value right there. All right, g of 5. Let's see. So g of 5 from this graph. So we locate where 5 is on the x-axis, and then we go up to the graph and find the point that has that x value, which would be that point right there. So g of 5 would be equal to 3. G of 2, well, notice at x equals 2, you're located right here, and notice the graph is actually on that point right there. And so g of 2 is equal to 0. G of 0. So when x is 0, so this is x equals 0 is the origin right there. And what happens? You go down, and so g of 0 would be equal to -2. And then, don't get fooled here. G of -3, well, you're going to -3 on the graph. But what happens at -3? That you have that open circle for the x, at that x value right there. Right? That point is actually not part of the graph. And so what would we say here? -3 is not in the domain for this function. So you don't get anything for g of -3, right? That's not a defined value right there. Right? So don't get fooled by a problem like that. All right, so hopefully we're doing well here. I don't think there's any, if there's any questions, remember to shout out. And so far I think we're good. All right, so our next graph here is going to look like this. So let's say we have the graph goes through the point 0, +4, sorry. 0, 4 right there, and goes through those 2 points right there, and you have this graph looks like this. This is a parabola that opens downward. like that. All right, so that's our graph. So we want to look at the domain and the range on this. Now again, notice in this graph you have arrows pointing down in both sides right there. And so that tells us that this graph continues on like that forever. So that means it's continuing to go down, and it's also continuing to spread out at the same time. So it's doing both things. Okay, so first of all, is this a function? That's our first question. And yes, this is a function because the graph passes the vertical line test. Okay, so the graph is definitely a function. Now, does it, so let's write down the domain and the range. And since it's a function, let's name it. We'll name it h. So we want to look at the domain of h and the range of h. Let's write that right here. So the domain of h and the range of h. So now what happens is you're walking along the x-axis, and remember this graph continues to spread out. So when you're walking along the x-axis, well, you know, at first you might say, well, let's like -4, for example, you might say is not part of the domain for this function, but it is. Because eventually, what are you going to do? You're going to see this graph right here because the graph continues to spread out forever. So somewhere over here, you're going to see the graph. And in fact, at -6, it's going to be the same thing. Somewhere, way over here at -6, somewhere you're going to see the graph. You know, who knows where, but maybe like right there. Right? The graph is going to continue to spread out. And so notice that's going to happen in both directions. And so no matter where you are for this graph on the x-axis, you always see the graph somewhere. Right? No matter where you are, for every x value on the x-axis, you're going to see the graph somewhere. And so what's the domain? The domain in this case is going to be all reals. So when you write all reals here, you can actually write that out in words, all reals for the domain. In interval notation, what you would do is you'd write -infinity to infinity. It means it goes infinitely far to the left, infinitely far to the right, everything in between as well. So the domain in this one is all reals. -infinity to infinity. And remember, you put parentheses around the infinities. All right, now the range has some things in common with the domain here. First of all, those arrows are pointing downward, so no matter how far down I go, right down this direction, somewhere you're going to see the graph, aren't you? Right, you see the graph maybe right there and right here at that y value, and maybe not quite that far there, but maybe like right about there. And as you, no matter how far down the range you go, or the y-axis you go, you're always going to see the graph somewhere. So the range is going to go all the way down there to -infinity. So if you're sketching this or shading this on the y-axis, you're going to have an arrow here. It means it goes forever in that direction. And you see the graph, and you see the graph, and you see the graph, until you get to 4 right here, and then you stop seeing the graph after 4. So there is a restriction on the range in this problem, and the range would go, and you always go from bottom to top on the range. Always, always, always from the bottom to the top. So -infinity, right, so it means infinitely far in the negative direction on the y-axis, all the way to 4 on the y-axis, and then you put a bracket right there. And so there's our range, -infinity to 4. You never ever put a -infinity on the right side of interval notation. It only goes on the left side. All right, so there's our domain and there's our range. And this is our function h. If we look at a little bit of functional notation here, if we look at h of 0, we see that h of 0 is equal to 4. Right, when x is 0, the y value is 4. H of 2, when x is 2, that's this point right here. And the y value is 0, so h of 2 is equal to 0. And h of -2 is also equal to 0 for the same reason. That point is on the graph. All right, so I think we've kind of analyzed that one pretty well. All right, so our next graph, and again, I'm not seeing or hearing any questions here, so I'm assuming that everybody is kind of following this okay. So our next graph all right, let's have a look at this one right here. So let's say we have a graph that goes through that point right there, 2, 0. Comes like this, and like this. And there's our graph. All right, so now, first of all, is this graph represent a function? And the answer here is no, this one's not a function. This graph fails the vertical line test. And so the graph is not the graph of a function. All right, if we look at an x value right here, like at the x value 4, right, we see that this graph fails the vertical line test. And so this graph does not represent a function. We would not name it. We're not going to look at function notation here because we don't use function notation for a relationship that's not a function. We can write the domain and the range, though. So we don't put a subscript on the domain and the range. We just put a D and an H for domain and range. So we can talk about the set of x values and the set of y values. So this is still some practice here. And so for the domain, what happens? We start seeing the graph at, let's see, as we're walking along the x-axis, right? We don't see the graph, we don't see the graph, we don't see it until we get to x equals 2. And then we start seeing the graph afterwards, for every x value afterwards, because of those arrows. And so the domain is going to be bracket 2 to infinity. And then for the range, well, in the range in this problem, because the graph continues to spread out forever, remember, it's not only going to the right forever, but those arrows also imply it's spreading out forever. No matter where you go on the y-axis, you're always going to see the graph somewhere. Maybe way off the screen, but somewhere there you're going to see the graph. And so this is a graph where the range ends up being every y value in both directions, right? So there's an arrow there and an arrow there. And so the range in this problem is going to be from negative infinity to infinity, like that. All right, so is it a function? No. Do we use function notation here? No. But we can talk about the domain and the range for this graph, all right? All right, so I think we're doing good. So let's look at maybe one more problem, a kind of graph that you might see in college algebra when you're graphing more complicated polynomial functions. And really, for what we've done now, this is not going to be that hard. Hopefully, you'll find that this is an easy problem compared to what we've been talking about. So let's say we have a graph, and I'm just kind of identifying some points here. And so this graph looks like this. This is actually a typical 4th degree polynomial graph. So you might see a graph like this in college algebra. Well, you definitely will see a graph like this in college algebra. So, all right, domain, well, first of all, is this graph a function? So we put a function question mark, and the answer here would be clearly yes, the graph passes the vertical line test. So we can name this graph, so we'll name it f for our function here. All right, does this graph, or let's talk about the domain and the range then for f. So the domain for f, well, those arrows on both sides, right? That means that the graph continues to spread out left and right. Not only does it go up, but it's also spreading out from left to right. And so the domain for this graph would be from negative infinity to infinity. No matter where you are on the x-axis, you would always see the graph somewhere. Now with the range, there is a little bit of a restriction on this graph, because this point right here, let's see, the coordinates for this point are at 1, 2, 3, 4, and then 1, 2, 3, 4, 5, -5. 4, -5 is their coordinates for that point. And so on the range, you do get a restriction here. The first time you see the graph is here as you're climbing up the y-axis. The first time you see the graph is here at -5. And then you start seeing the graph, and notice you see the graph twice here. It doesn't matter how many times you see it on the y-axis, from the y-axis. As long as you see it once, that value is part of the range. And so you see it twice, you see it twice. Notice right here, as the graph starts looping around, here at that y value, at the y value 1, you see the graph 4 times. That doesn't matter. And then right here at this y value, you see the graph twice right here. Right? It doesn't matter how many times you see it. It's just do you see the graph as you're moving from left to right. And so the range for this function starts at -5, and -5's got a filled in dot there, so it'd be a bracket around the -5, and then this would go to infinity for the y's right here. All right, so there's our domain and range for this function. And we could also read some function notation or evaluate some function notation based on our graph. So for example, f of 4, right? We've got that point 4, -5. There's x equals 4. So f of 4 would be equal to -5. F of 2, x is 2 at this intercept right here, and so f of 2 is 0. F of 0, when x is 0, you're talking about this point up here, and that would be at 2, so f of 0 is equal to 2. F of -3, here's x equals -3 right here. And the y value, you look up at the graph, and the y value is at 1, so f of -3 is equal to 1. So I'd certainly like you to be able to read function notation from a graph. I think that's something that if you could walk into college algebra and you could do these 3 things, it would be awesome if you walk into college algebra and you can do this. If you can look at a graph and tell me whether it's a function or not using the vertical line test, that's great. If you can take a graph and you can write down, at least with basic graphs like these, you can write down their domains and ranges in interval notation, that's awesome. If you can read function notation from a graph, that is awesome. Those are all wonderful things that you could, if you started out being able to do that in college algebra, you'd be one step ahead of the game. There's no question about that. So hopefully, and as you go through this, notice it's really not that hard, right? Compared to some of the things we've done this semester, this is definitely not the hardest things we have worked through during the semester. So you ought to be able to do these kinds of things. In college algebra, you look at being able to read other things from graphs besides just the function notation and the domain and the range. There's other things that you're interested in for these functions. And so these basic things would be good to be able to do right away at the beginning of the problem. All right, so we've got, let's see, we've got domains and ranges, a little bit more complicated ones there. We've read function notation. So I want to go flip back to my little outline for the class for today. So we've done more with domains and ranges. We're talking about reading other information from graphs, which we've been doing. And so now we want to look at graphing functions and look at some things we're having to do with graphing functions. All right, so graphing functions. First thing I'd want you to be able to do with graphing functions is be able to make a sketch of a graph simply by making a table of values and plotting points. Just be able to do that. Now that is not, in general, a good way to sketch a graph because some graphs are so complicated that just plotting some points, it's hard to know how many points to plot to get an accurate graph. So you're going to have to be able to find other things about a graph, other ways besides plotting points. But plotting points is the most basic thing. And so let's talk about that. So graph by plotting points. That's what we're talking about. And so when I'm talking about plotting points here, I'm just talking about making a t-table, getting some representative values, and being able to sketch a graph. So the first one we want to look at, let's see. Let's say we have f of x is negative 3x plus 8. Negative f of x equals negative 3x plus 8. All right, so if you're going to plot some points here, make a table of values, this is a linear function, right? Because the x is raised to the first power, right? Remember, f of x equals negative 3x plus 8 is the same as y equals negative 3x plus 8. So we know that this is linear. We talked about linear equations already. All the terms are first-degree terms. The x's and y's are raised to the first power. And so we know that the graph's going to be a line on this problem. And this kind of problem we've already talked about, actually, right? So, you could use a representative sample of points, and in many cases, a lot of cases, you would just choose the points that you want to use, but you have to kind of base it on the graph you're dealing with. So let's look at this set of points right here. And I just kind of picked this based on points that would fit on my graph more than anything else. So when x is negative 1, what are we doing here? We're finding f of negative 1, right? And f of negative 1 is negative 3 times negative 1 plus 8. And so that would be 11. That'd be 3 plus 8 or 11. F of 0, the next one. Right? When x is 0, you get f of 0 here. So this is negative 3 times 0 plus 8, which is 8. And the next one is f of 1. So you have negative 3 times 1 plus 8, where all you're doing is substituting these x values in for x, right? And so that gives you 5. F of 2 would be negative 3 times 2 plus 8. It's negative 6 plus 8, or 2. And then finally, f of 3 would be negative 3 times 3 plus 8, or negative 1. All right, so you ought to be able to get a decent number of those points on a graph here. This is a graph that's in the equation's in slope-intercept form. You know the slope's negative 3, so this is a pretty steep line, and the y-intercept is at 8. So it's a pretty steep line here. So you've got 1, 5, 1, 2, 3, 4, 5 is way up here. 0, 8 is way up here. 2, 2 is here. And then 3, negative 1 is here. And so here's our graph. Pretty steep line that's slanting down as you go from left to right. Right, and there's our graph. By the way, once you sketch the graph, I would certainly want you to be able to write down the domain and the range. And if you think about it, for a slant line like this one, the domain is always going to be negative infinity to infinity. And the range is always going to be from negative infinity to infinity. For slant lines, this is always true, that they're always both going to be all reals. Because of those arrows, you're saying that the graph goes infinitely far in those directions. So it's spreading out. So in other words, it's moving from left to right, and it's also moving up and down forever. So the domain and the range for a line is always going to be all real numbers. All right, so that's a pretty simple graph. Next one. Let's say we have f of x is equal to negative 2. Now, this function right here, just a constant like this, and I think I've alluded to this once already last week, but this is called a constant function. F of x equals negative 2, and when you are looking at function notation here, what you're saying is that no matter what value you try to substitute in here, so if you look at f of negative 2, you get negative 2. And f of negative 1 is negative 2. And f of 0 is negative 2, right? That f of anything for a constant function is going to be the same value. In this case, negative 2. You get negative 2 as an answer for all of these. And so the graph here, we've talked about this kind of graph already, but For a constant, remember f of x equals -2. Also, another way of writing that is it's just y equals -2. Right? And we've talked about that already, that functions that, or equations that are written as y equals like this, these are just horizontal lines. Right? And here you got 0, -2, 1, -2, 2, -2, -1, -2, and so on. And you get that graph for this one. So all constant functions graphs are horizontal lines like this. Again, that'd be so awesome if you knew that going into college algebra, that when you have a constant function like this, that your graph is going to be a horizontal line automatically. The domain for this function, it is certainly a function. It passes the vertical line test. The domain's -infinity to infinity. The range, on the other hand, you cannot write in interval notation because there is only one value in the range. And the only value that's in the range is -2. So you just simply put -2 in braces, and you would not use interval notation there at all. And you'd write it just with the number -2 there for the range. All right, so let's look at some functions that are not linear, not lines, and let's look at some examples there by plotting points. So f of x is equal to, next problem I want to look at, 1/2 times x squared. F of x is equal to 1/2 times x squared. Because of the square on that, this is not a linear function, right? This is a degree 2 equation, so this is not linear. So this graph is not a line, and you'll very quickly see that as you start plotting points. So we're looking at x and y, and let's look at -2, -1, 0, 1, and 2 for x values. Those are frequently a good place to start, and then if you feel like you need more points, you can always use more when you're plotting points and making a t-table like this. So what are you doing here? You're looking at f of -2, f of -1, f of 0, f of 1, and f of 2, right? That's what you're trying to evaluate for this particular function. Now, this is a place where I frequently see sign mistakes here, so you have to be really careful. So this is this f of -2. What are you doing? You're substituting -2 in place of x, right? And so this is 1/2 times -2 squared. -2 squared is +4 times 1/2. And so you get 2 here for the value, for the function value. F of -2 is equal to 2. A lot of times I see sign mistakes there. F of -1, right? So you substitute -1 in for x. And so you have 1/2 times -1 squared. -1 squared is 1 times 1/2 is 1/2. All right, you can estimate where that is, easy enough. F of 0, you have it 1/2 times 0 squared. But 0 squared is 0, times 1/2 would be 0. And so you have f of 0 is equal to 0. It means the graph is going to pass through the origin. Now notice when you look at f of 1 and f of -1, you get the same answer, because on one of those you're squaring -1 and the other one you're squaring 1, but you get the same answer either way. So this is going to be 1/2. And then f of 2 is the same thing as f of -2. Because you're squaring, you get the same answer either way. So this is 1/2 times 4, and so you get 2 as the answer there. All right, so you're getting some repeated y values on this graph. That's okay. Remember, repeated y values are not a problem. And then we're looking at the graph, and you can already tell from these points that this is not going to be a line, right? You have -2, 2 is this point right here. -1, 1/2 is located right about there. 0, 0 is there, and you can already see that with those 3 points, that these points clearly are not lying on the same line. And then you've got 1, 1/2, and okay, for sure now you know it's not a line. And then 2, 2 is right here. This graph is a parabola. If you felt like, if you still felt like you weren't sure it was a parabola, and you felt like you needed to do more points, there'd be nothing wrong with doing that. You could go on to -3 and 3. And I mean, that would be absolutely nothing wrong with that. It's never a problem to look at more points on a graph if you're not sure what it's doing. So with -3, you're looking at f of -3, which would be 1/2 times -3 squared. So that'd be 1/2 times 9, or 9/2. And remember, 9/2 is 4.5, 4.5. F of 3, this is exactly the same answer, isn't it? Whoops, f of 3. So you get 9/2 there, or 4.5 on that one. So you have -3, if we look at where those points are, -3, 4.5 is right here, and 3, 4.5 is right there. And so now you're starting to really get a good idea that this is a parabola. When you've got all these points here, that you've got a pretty clear sketch here for this graph, right? You're going to look at parabolas more in college algebra, do some things with parabolas. These are actually important in applications. And so it's good to be able to start plotting these by hand like this. All right. By the way, in a parabola, this low point on the parabola, that point is called the vertex of the parabola. So in this case, the vertex is at 0, 0. I'm not going to ask you that, but nice to know going into college algebra. And that's one of the more important points on the graph. All right, so next graph we're going to look at. Let's look at f of x equals x minus 3 squared. And let's go ahead and say x minus 3 squared minus 2. Okay? All right, so let's look at plotting points to sketch this graph. Also, because of the square, this is clearly not going to be a line, right? This is not linear. And because of the square now, based on the first problem, you're starting to think, well, maybe this is going to be a parabola. All right, so, and you might feel after we plot our representative group of points here, you might feel like you need more points on this one. We'll see. So when x is -2, you've got to be really careful when you're evaluating these functions. So you're looking at f of -2 right there. And remember, all that f of -2 means is plot -2 every place you see an x. So this is going to be -2 minus 3 squared minus 2. And I would be really careful writing this out. Just take your time with this. Substitute in these values for x, and be careful with the arithmetic. I see this is not hard to do, but I see students all the time missing these because they make really careless arithmetic mistakes as they're substituting these x values in. You would be surprised at how many mistakes I see with these types of function notation problems. So really be careful with this. So notice in every case, for function value, what did I do? I substituted the value in for x, right? And now I'm going to do the arithmetic, right? And, just so you see, there's my x, and what did I do? Every place I saw an x, I substituted in my x value there. And here's the x value that you're substituting in. All right, remember, that's how you evaluate function notation here. All right, so let's do the arithmetic. Be really careful. So -2 minus 3, and that first one is -5. So this is -5 squared minus 2. Well, that's 25 minus 2. 25 minus 2, or 23. Okay, so that's a big y value. The next one, you have -1 minus 3 is -4. So this is -4 squared minus 2. That's 16 minus 2, or 14. It's gotten smaller, but still kind of off where we're going to be sketching the graph. The next one, you've got 0 minus 3. So you get -3 squared minus 2. So that's 9 minus 2, or 7. It's getting better. The next one, you've got 1 minus 3 is -2. So you have -2 squared minus 2. That's 4 minus 2, or 2. 2 minus 3 is negative 1 squared minus 2. So that's 1 minus 2, or negative 1. Now, if you plotted these points, you're going to find that you still are maybe unclear as to what the graph is looking like. I could actually put down at least some of these points right here. Let's see. I'm going to kind of maybe I'm going to actually put that axis over here like this. All right, so here's our coordinate system right there. All right, so I'll put this one in green because we're going to kind of impede into the other graph a little bit. So you have negative 223. Well, I think 23 may be off my graph, but at least negative 114 I could locate. So there's 2, 4, 6, 8, 10, 12. 14 is way up here, and you're at negative 114. So that's my point. It's way up there. All right, f of 0 is at 7. So 2, 4, 6. Here's 7 right here. So there's the point 0, 7. And then the point 1, 2 is right here. And then the point 2, negative 1 is right here. But, you know, I'm kind of unclear when I see those green dots there. I'm unclear as to what this graph is looking like. And so this is a place where I might, I suspect that it's a parabola, but I might use some more x values. I might use 3 and 4 here for x equals 3 and 4 and see if that gives me a little bit clearer idea what my graph looks like. So f of 3 would be 3 minus 3 squared minus 2. So 3 minus 3 is 0 squared minus 2, and so that gives me negative 2. Right, so at 3, I'm at negative 2. So that gives me a little bit better idea now of where the graph is. So at 3, I'm at negative 2 right here. All right, I go on to f of 4 next. And so that would be 4 minus 3 squared minus 2. So that would be 1 squared minus 2, and that's going to give me negative 1. And so notice now I start really getting an idea of what this graph looks like, that this is going to be a parabola, and the graph is now turned, hasn't it, at 4. If you wanted to, you could go on to 5, but you're going to find that with 5, you're going to get the same y value that we got a few minutes ago when we used 1. We're going to get that at 5, you're going to get 2, right, because the graph's very symmetric. So if you go through this arithmetic here, you're going to find that you're going to get 2 as the answer. So f of 5, you have 5 minus 3 squared minus 2. So 5 minus 3 is 2, squared is 4, minus 2, and you sure get 2 right there. Right, and so there's my parabola. Right, and so I needed to plot a few more points besides just negative 2 to 2 to get an idea of what that graph was going to look like. Whoa, I kind of missed it there. All right, so there's my graph. All right, the domain and the range. Remember, we've been kind of talking about the domain and range for a lot of these graphs. So what's the domain for this graph? And let's see, I'll put this at the very bottom here. Well, for parabolas that open up or down like this, the domain is always going to be all reals, negative infinity to infinity. It's just like a line, it's always going to be all real. So that's nice. The range for this graph, notice on the range, the first time you're drawing these horizontal lines, and the first time you see the graph on a horizontal line is at negative 2. So this starts bracket negative 2, and then this goes on to infinity like this. As you move up, you're going to see the graph forever going up like that. All right, so we plotted a lot of points in that one. Let's see, so I don't see any questions, so I'm going to continue on looking at some plotting problems where we plot points. So let's say I have f of x is equal to the absolute value of x plus 2 minus 3. All right, absolute value. We're going to look more at absolute value next week, by the way, to finish the semester out. But f of x equals the absolute value of x plus 2 minus 3. So let's look at plotting some points on this graph, and let's see what this looks like. All right, so if we use our representative group of points here from -2 to 2, by the way, let me remind you that absolute value means the distance a number is away from 0 on the number line. So the absolute value of 3 is 3, because 3 is 3 units from 0. But the absolute value of -3 is also 3, right? Because it's also 3 units from 0, just on the other side. And so, keep in mind that the absolute value always ends up being a positive number or 0. All right, so -2. Let's see, so we've got f of -2. So that'd be the absolute value of -2 plus 2 minus 3. And if you want to do the arithmetic now, that's fine. So that's the absolute value of 0 minus 3. The absolute value of 0 is 0. And so you get -3 as the answer there. All right, f of -1. You have -1, absolute value of -1 plus 2 minus 3. Remember, we're just substituting these x values in for x here. And so that would give you the absolute value of 1 minus 3. And so that would be 1 minus 3, or -2. F of 0. You get the absolute value of 0 plus 2 minus 3. And so 0 plus 2 is 2, so you have the absolute value of 2 minus 3. And so that gives you 2 minus 3, or -1. All right, so things seem to be going pretty smoothly here. Put in 1, f of 1 would be 1, absolute value of 1 plus 2 minus 3. So the absolute, 1 plus 2 is 3, so that's the absolute value of 3 minus 3. And so you get 3 minus 3, or 0. F of 2. You have the absolute value of 2 plus 2 minus 3. So that's the absolute value of 4 minus 3, or 4 minus 3, or 1. Now let's see where we are with this, and let's see if we need any more points. And so in this graph, if we start plotting the points that we've got, let's see, so I've got -2, -3 is here. -2, -3, -1. Right, so -1 gave me -2. So -1, -2 is here. 0 gives me -1. 1 gives me 0. And 2 was 1. All right, so all those, so what does it look like I have here? It looks like I have a line on this, for this graph. And this is a really good example of how plotting points can really lead you into trouble if you don't know a little bit more about what's going on. See, I know going into this problem, I know, because it's an absolute value, what this graph is supposed to look like. And I know it's not a line. And I know what its basic shape is. So I know that I need more points, and that the points I picked are not going to be sufficient here. And this is a good example of why plotting points has got to be supplemented with other things if you're going to make it a successful way of sketching a graph. Now, if you use 3, let's just go one positive number up. If you use 3, you see that it looks like the same thing is happening, that the graph just continues to get bigger by 1 each time. And, so you get 5 minus 2, 5 minus 3, and you're going to get 2 right there. So that hasn't changed anything. But what I do want you to do is go on to negatives and look at -3 and -4 and see what happens here. And all of a sudden, your mind is going to get changed about whether this is a line. So f of -3 gives me the absolute value of -3 plus 2 minus 3. So that's the absolute value of -1 minus 3. But the absolute value of -1 is +1. So this is 1 minus 3, or -2. Look where that point is. At -3, you get -2. And notice that's that point right there. If I look at f of -4, I get the absolute value of -4 plus 2 minus 3. That's the absolute value of -2 minus 3. That's 2 minus 3, or -1. It's 2 minus 3, or -1. And so notice this graph has started kind of going back up as we're going off to the left here, like that. This graph, see, and I knew this going into the problem, that absolute value graphs like this are these kind of V-shaped graphs like this. And so I knew that I needed more points to sketch the graph like this. This is a common shape for an absolute value graph. All right, the domain on this function is, because the arrows are like they are, this graph just continues to spread out forever. So this is -infinity to infinity. The range on this graph, if we're looking at horizontal lines and we're climbing up the y-axis, the first place we see the graph is here at -3. And so the range on this graph is going to be from bracket -3 to infinity. That would be the range for this graph. All right, so we've looked at some good examples here for plotting points to sketch graphs. And you can see that sometimes you're going to have to make some adjustments on what you do when you're sketching these graphs. All right, I'm going to look at one more graph, and then we're going to finish by looking at a couple of problems where we're looking at finding x and y intercepts. So one more graph. So I've got about maybe 10 more minutes left here. So f of x equals the square root of x minus 1. Now this is a graph that's really different from what we've seen before, because there's actually a restriction in the domain. And so there's some x values I can't use in this graph. See, if you try to use x equals 0 here, for example, f of 0 is the square root of 0 minus 1, which is the square root of -1. The square root of -1 is imaginary. When we are graphing functions in the plane, we are only using real numbers. We are not using imaginary numbers. There's no place to put imaginary numbers on these graphs. And so what this means for us is that 0 is not in the domain. And notice if you use anything less than 1, this would be true. So any x value less than 1 would give a square root of a negative number. Like that, and so it's not in the domain. And so in fact, the very first x value you can use here, when I say if you're going from left to right, would be x equals 1. F of 1 would be okay, because that would give you the square root of 1 minus 1, which is just the square root of 0, which is 0. And when you use x equals 2, that one's going to be okay. You get the square root of 2 minus 1, which is the square root of 1, which is 1. 3, no problem there. You get the square root of 3 minus 1, which is the square root of 2. Square root of 2 is not a problem. It's just that you just have to estimate it, and it's about 1.4. The next x value that you could pick that would give you a nice y value would be 5, because you'd get the square root of 5 minus 1, which is the square root of 4, which is 2. Right, and that's actually going to end up being enough points to make a sketch of this graph right here. This graph goes through 1, 0 right there, but you can't pick anything less than 1, any x value less than 1, so the graph actually stops at that point, 1, 0. And then you have 2, 1, 3, 1.4 is like right there, and then 5, 2 is here. This graph is actually, looks like this and is the upper half of a parabola that's opening off to the left, off to the right, rather. Notice that this graph actually stops at the point 1, 0. The domain for this function would be from 1 to infinity. As we walk along the x-axis, the first x value we see would be at x equals 1. The range for this graph, as you're going from bottom to top, the range for this graph, the first place you see the graph would be at y equals 0. And then you see it for every x value after that. So the range goes from 0 to infinity. All right. The last thing I want to briefly talk about here is if you have a function, let's say a function written, and it doesn't matter how it's written, by the way, but let's say I have a function that looks like this one, f of x equals x squared minus 9. I might ask you in a function like this to find the x and y intercepts. Now remember what that means, because we've talked about that with lines, that when you're talking about x and y intercepts, it's what you're doing is the x-intercept, you're substituting in 0 for y, and for the y-intercept, you are substituting 0 in for x. And also remember that in this function, f of x equals x squared minus 9, that's really y equals x squared minus 9. So notice for the x-intercepts, this is actually slightly more complicated than with lines. With the x-intercepts, you're substituting 0 for y, and you get a quadratic equation. You get 0 equals x squared minus 9. And so that can happen. And you could solve that equation either by factoring or the square root method. The square root method would be the easiest. Just add 9 and then take the square root of both sides of the equation, and you get plus or minus 3. So this is a graph that has two x-intercepts. The x-intercepts for this graph, this function, are going to be at 3, 0 and negative 3, 0. And the y-intercept, how are you finding the y-intercept? You're substituting in 0 for x. So in other words, by the way, with function notation, what that means is you're really looking at f of 0. So they get 0 squared minus 9 or negative 9. The y-intercept's at 0, negative 9. There's one y-intercept. So at the x-intercepts, what are you doing here? You're setting the function equal to 0. In other words, you're substituting 0 for y. For the y-intercept, what are you doing? You're substituting 0 in place of x. You're looking at f of 0. All right, let me look at one more function like that, and then we would be done for the day. So let's say we have f of x is equal to x squared plus 8x plus 15. Okay, so the x-intercept, what are you going to do? You're going to set y equal to 0 in the equation. And so, in other words, you're setting the function equal to 0 because the f of x is the same thing as y. And so that's the equation you've got for the x-intercepts, is 0 equals x squared plus 8x plus 15. That is a quadratic equation, and that is factorable. Not hard. It's x plus 3 times x plus 5. In these problems, I'm not going to give you anything that factors that hard at all. I just want you to be able to do basic problems like this where you're finding x and y intercepts for some basic functions like this. So this graph has two x-intercepts at negative 3, 0 and at negative 5, 0. Like that. Right? How do we find the x-intercept? We set y equal to 0. And when we set y equal to 0, we're really just setting the function equal to 0. The y-intercept, what are we doing here? We're setting x equal to 0. So what we're doing with a function is we're really just looking at f of 0. And f of 0 is super easy here in this problem. 0 squared plus 8 times 0 plus 15. F of 0 is just equal to 15. And so the y-intercept's at 0, 15, like that. So I wanted you to be able to find a few problems like that, where you're finding x and y-intercepts. All right, so that finishes up what we wanted to do today with functions. So a couple of things here. First of all, your homework, I already have that written out. This x and y intercept stuff, there's not very many problems for practice in the textbook. So here's 10 practice problems for finding x and y intercepts for the graph of the function, just like we just did. And then here's some textbook homework also. Remember, this is the intermediate textbook, and this is section 3.6, problems 337 through 379. Any of those problems would be great practice problems. All right. Remember that the exam 3 review is online. Remember that I have some online office hours tonight and on Sunday. Does anybody have any questions that's online with me right now?
No.
All right, that was an enthusiastic no. So no questions. Then I want everybody who is with me live today and also is watching this video later, have a wonderful Thanksgiving. Have a safe Thanksgiving. Hopefully you get to see some family over the week. Please don't hesitate to email me or go through WebAssign and message me. I will be checking email and WebAssign during the weekend and be answering questions like that. And so start getting ready for exam 3. Have a great week. And I will, our next live lecture, remember, will be next Tuesday. So have a great Thanksgiving. Thank you, Jose.
You too as well.
Thank you very much.